Good afternoon, everybody. While the flexible substrates may use plastic for smaller displays, glass will be there for the larger displays, especially TVs, for some time to come, unless the RGB OLED comes in future. And Mike, while you may discount glass, but glass will always carry the OLED polyimide plastics as a carrier substrate, and also will protect OLED devices. So with this, I'll begin my presentation. In order to fully understand the importance of glass for displays, it is important to know the relative place of glass in the entire supply chain of displays, and in particular liquid crystal displays. Now, if you look at the bill of materials of a panel, LCD open cell, you can see clearly that glass occupies the top position with 1/3 of the bill of materials by the glass substrate. And with this in mind, if we look into the operating profits, even in that area, in that region, glass enjoys the maximum operating profits with staggering 46%. And if you look at the glass market over a period of next few years, up to 2023, we can see that the glass market is going to grow by 5% annually. While the glass market is going to grow 5% annually, the average selling price is equally going to drop 5% annually. Therefore, the glass, in terms of revenue, would be stable at about $7.5 billion for the next 5 to 10 years. Now, glass is basically, this LCD display in particular is a sandwich of two glasses. The rear substrate glass basically is used for putting the arrays architecture, and the front substrate glass uses the color filter. And then you put the liquid crystal in between and make a sandwich, which is called the cell. And then you cut the glass and put polarizers on top, and the driver circuit, which makes the open cell. Now, what are the requirements from glass? Why this glass is so important? And the reason is that the glass must match the properties of silicon, which is thin film transistor. And the most important property is the thermal expansion coefficient of silicon, which is 30 × 10⁻⁷ per degree Celsius. And the glass must have the thermal expansion coefficient close to it. And the strain point should be high because the working temperatures during processing are pretty high. So the strain point must be more than 600 degrees Celsius. Ionic content must be less than 0.1%. This is the key. Because any ionic contamination will then ruin the TFT performance. And now, coming back to the typical, usual, normal glass, soda lime glass, it has about 14% to 15% alkyl content. That's the reason why it is so easy to melt at about 1400 degrees Celsius, which means that if this glass has an ionic content of less than 0.1%, this glass will be like a silica glass, which is melted at about 1700 degrees Celsius. Hence, these glasses are extremely difficult to melt. This is a great challenge to melt these glasses. And then the fourth point, which is the peak to valley flatness must be in nanometer levels, which is equivalent to allowing only 1 inch of wave in an ocean depth of about 3 kilometers. And again, one more important point is the size. When I went to Japan way back in 1992-93, the size was only generation 2 and 3, about 0.5 meter by 650 millimeter. And now it has gone to about 100 square feet, generation 10, which is about a size of a small room of our children. So these factors, these last two particular factors are very important and so difficult to achieve that there are only 4 makers in the glass, makers of glass in the world. only four: Corning, Asahi, NEG, and ASI. Other small players are coming, but they have not achieved the success so far for higher generations. Now, how the glass makers make the glass? While I told you that melting is very difficult, it can still be overcome by adding oxy-fuel melting or employing very high-tech melting techniques. However, forming is most important because during forming, the flatness is frozen in. Corning has come up with the state-of-the-art process of forming, which is by using fusion process. In the fusion process, you use an isopipe, the glass flows in. Isopipe means same hydraulic flow rate, which means when the glass flows in, the glass flows out of the pipe equally in volume when it goes down. So the glass is extremely flat, and when the glass comes down from both the sides, it meets at the root, it fuses at that point, and that is why it is called a fusion process. While all the three glass makers out of four use this process of fusion, Asahi makes it by float process. In float process, the glass melts over molten tin, which has a density of about 6.9 gram per cc, and glass has a density of about 2.4 gram per cc. Hence, it floats on tin bath, and when it comes out, it's pretty flat. But still, it is not as flat as the requirement of LCD. Therefore, the fusion process, the float process, the bottom side has to be polished. Two reasons. One is there is some tin contamination, and also the flatness is not good enough. So then they touch polish the glass, and that is why the glass produced by float process is more expensive. Now, I told you, I just gave you a hint of the barriers, that there are two main barriers that I explained: flatness and difficult to melt. So these two main parameters have caused, there's so much technology that is involved to overcome these processes that it is heavily IP guarded. And then design of the machines, design of the isopipe, and then knowledge and patent of the glass compositions, and then very long gestation periods. One Korean company, two Chinese new companies have been trying for the last 10 years. And still, the yields are not as good as the top four makers, and the quality is not as good as the top four makers. And then the past failures. Schott from Germany tried. Two companies, Pickview and COTC in Taiwan, tried and failed. I'll give you a beautiful story. When I went to Japan about 24 years ago, in 1993, the display glasses used to break. And my boss used to come from Osaka, would bring a bag and would give it to me, saying that, Segal-san, kore wa Segal-san no tame ni omiyage desu. Means I have brought souvenir for you from Osaka. And I would open the bag. It was broken glass. I was given the responsibility to figure out what is happening. So while we are talking about the glass breakage, there were 4 or 5 main problems at that time which were easily solved by tweaking some processes. For example, shrinkage. By doing good annealing, you could get rid of shrinkage. But breakage problem of glass was very difficult to resolve. And at that time, fracture toughness was one tool that was available for estimating the failure behavior. But fracture toughness measurements used to take at least 10 days because 7 days would be gone for sample preparation. So by the end, the sample preparation would involve so intricate things that while the samples would come back and you would do the testing, there would be some artifacts of experiments, and you would not trust the data. So while I was working on it, I found that when you did indentation using diamond, pyramid, at certain load, window glass would not crack so easily, but the display glass would crack very easily. The crack length at the 4 corners of the deformed indentation, the crack length to the diagonal ratio was very high. I jumped and I went to my boss. I said, I found it. And I termed it as brittleness index of brittleness, which was C by A ratio. And I found that there were parallel lines going around. The lowest line, the lowest brittleness was soda-lime glass, the window glass. The highest brittleness was plasma TV, and in between you had LCD. So while we were confident that this was a faster technique and we could change the glass compositions very easily, we were not satisfied. Because at that time, there was a very good work done by Brian Lawn and Marshall from, at that time, NBS, National Bureau of Standards. He had come with a definition of brittleness called hardness to fracture toughness ratio. But again, fracture toughness was very difficult to measure. But however, I found that we could correlate C by A ratio to brittleness by this equation. This is my equation published in Journal of Material Science Letters in 1997. So using this technique, we found very fast the effect of each component of LCD and display TVs, and brittleness improved. We got rid of cracking completely. And then we also found that for commercial glasses, if you look at this data, for commercial glasses, there was, if you plot density versus brittleness, there was a minimum in brittleness at the density of 2.38 gram per cc. And these two data points, these two, they are basically laboratory glasses and unstable. Therefore, in all commercial glasses, the brittleness was lowest at 2.38 gram per cc. And I found, when I published this data in 1998, 1999 or 2000, Corning came up with a glass called Eagle 2000. And the density was 2.38 gram per cc, with the least brittle glass. So, in conclusion, the glass is the most valuable entity in the entire supply chain of displays. Only 4 major glass makers are there in the world. And the reason why few glass makers is because the technology is highly IP guarded, and because of the past failures. And our work helped to reduce the breakage problem of glass, and this ratio of brittleness is very fast, or of measurement of brittleness is very fast and convenient, and now it is published in the textbooks also. And then we could use this method to design new glass compositions, even for touch panel glass. I was invited to Korea by Korean Ceramic Society annual meeting. At that time, I was told by Samson Corning that this method was used, or this concept was used to design Gorilla Glass. And then now they are also using this concept in designing new dental implants and bones, artificial bones, etc. And now this work was considered to be the top work, one of the top works by American Ceramic Society in the last 100 years. Yeah. So this I will. And in the fab that you see here, we will also have a glass plant. This is the glass plant. Yeah. Great. Thank you.
So now, by the way, when we say plastic is the plastic on top of glass. So we need the glass.
But only for during processing.
Only for the processing. But we are not actually shipping the glass. So when we all talk flexible in the morning, we're not doing any floppy processing. It's on glass. So we need you. Okay? So anyway, thanks for the ratio, which I didn't know. And you're interested in 2,386 at the front. What was that? In the equation.
Oh, there was a constant, it's a very interesting topic.
Okay, well, we need some beer for this.
I had sleepless nights for about 7 to 8 days, and it turned out that it's basically a Young's modulus to hardness ratio. E to the power half divided by h to the 1 by 4.
See, there you go. So there are properties of numbers very important in India. 1089 is an important number. We'll go to that later. 2386 may be a different one. So today you heard a cross-section of talks. You know that 10 years from now you'll be having your TV in your pocket, all folded inside, rolled up, not rolled up, or somehow it'll be in your pocket. And at the time you want to use it, you will click it like an umbrella, click and it opens up and you see that is where we're going to. So we have all the fun in the display industry making very interesting things out of what is already available, but making it more flexible, form factors and all that. So you heard a lot of things today about variety of topics. And we wish you all well, the Indian initiatives here. We want to come and work with you and from the display industry perspective and make you successful in whatever way we can. And we can also learn during the process of equations like you mentioned. Okay. So with that, Ashwini, tell us what next is.
So I think Dr. Garg will do the honors.
Okay.
And when you have a tea break,
Uh-huh.
we will have we will have a networking session for the we meet again around 5:15 or so.
Okay.
We go for the final session.
Okay.
Mars and Mr. Paul and I.
All right, good. So let's, we got the,
Yeah.
oh,
So this time I'm doing the honors. You please.
okay, you do that. I'll sit down.
Thank you very much. Starting from there. Harit, we have a special mention for you because with this we are also giving a certificate of membership to ISA. Right? Thank you very much, man. Wonderful presentation. You brought us into the market of royalties. Yeah, please. Thank you very much. And I'm not giving you, I'm only giving you a hug. Let's break for tea, and then we come back.
Not 10, no.
Okay, I think the audience can come back because we have the IoT security session here and the
Whoever wants to
and
meet the display
SID,
guys.
SID team will just have a networking session.
Yeah.
That is the plan.
Okay, so we are available outside, and we're going to show a lot of willpower and drink some tea.
Yes.
Unfortunately, there's no beer here.
So soak in the
but,
sun.
Thank you.